Yes, sir.
Okay. So the reason we have seen it's because of the stability of the carbocation which forms in the intermediate stage, right? So this is the reason we have seen. So when we treat this N-propyl chloride with AlCl3, it generates the primary carbocation, and this primary carbocation is not stable, so it goes internal rearrangement. The hydrogen shifts to the primary carbocation and it generates the secondary carbocation. This is stable, and this secondary carbocation will be attacked by benzene ring and it generates the cumene. So this is the thing we have seen, and today we will see the Friedel-Crafts acylation. Okay, so Friedel-Crafts acylation means the starting material is different, that is in alkylation we have seen simple alkyl chloride, but here alkyl chloride or alkyl halide, but here we have a acetyl chloride or some acyl chlorides. So the acyl chloride means it has the COCl functional group. Okay, so that means acid chloride. Then the catalyst, the reagent is same, that is the anhydrous aluminum chloride. So first, how the aluminum chloride generates the carbocation that we see. So when we treat this acyl chloride with anhydrous aluminum chloride, it generates the acylium ion. Okay, so that is like this CH3COCl. So by abstracting the chlorine from this acyl chloride, it gives AlCl4 minus and it produces the acylium ion. So this acylium ion acts like exactly like a carbocation. So this will be attacked by the benzene ring and which produces the acetophenone, that is the ketone, aromatic ketone. Okay, so this is the Friedel-Crafts alkylation reaction. So if we have a blackboard, then I would have written the mechanism. So please carefully see the steps. So these steps involves three steps. Steps A, formation of the carbocation or acylium ion. In this case acylium ion we say only for this Friedel-Crafts acylation reaction. And step 2, this acylium ion attacked by the benzene ring, and this will be stabilized by the resonance structure, that is the sigma complex. This we will see in the last unit, that is the unit 5. Okay, we will see detailedly in the aromatic substitution reaction. Okay, the mechanism and the resonance structure we will see detailedly. Now you just see in the second step attack of benzene ring on acylium ion, and in the third step the abstraction of proton by the AlCl4 minus. Since it is a negative charge, it will abstract a proton and to neutralize or to stabilize the aromatic ring or to generate the aromaticity of the benzene ring. It has to give one proton. Okay, and then finally it gives the product, that is aromatic ketone, that is the acetophenone. So total 3 steps. Okay, both in our Friedel-Crafts alkylation and Friedel-Crafts acylation, both it follows the 3 steps. Okay, so next is the pinnacle pinacolone rearrangement. So this is very very important rearrangement. Please have a note and please listen carefully. This will come for your exam. Okay, pinnacle pinacolone rearrangement, this is very important. This reaction will come even after your masters, when you are preparing for your CSIR or GATE exam. That time also this is a very important, this will come definitely. Okay, so the pinnacle means it has the 2 hydroxyl group, the starting material pinnacle. The both hydroxyl groups are in the alpha carbons. Both will be in a adjacent carbons. As you can see here in carbon 2 and 3, in adjacent carbons, each carbon has one hydroxyl group. Okay, so this is common name is called pinnacle. Okay, 2,3 dimethyl butane 2,3 diol, the common name is a pinnacle. So when we treat this pinnacle with very strong inorganic acid, okay, H2SO4 we used here. So I said yesterday, if we use inorganic acids to alcohol, what will produce? Anyone respond? What it will produce? Yesterday I said, students, anyone try to say answer? board is not visible. Sorry. Okay, now you can able to see, right?
Yes.
Okay, sorry for that. I was giving too much detail. Okay, now I give the Friedel-Crafts acylation. Okay, so as I was explaining that three steps, right? So this is the three steps. Acetyl chloride, which generates the acylium ion using a anhydrous aluminum chloride, AlCl3, as the catalyst. So AlCl3 abstracts the chlorine, and then it generates the acylium ion. Okay, and then the second step, the benzene abstracts the acylium ion, not abstract, the benzene attacks the acylium ion and it generates the sigma complex. And in the third step, abstraction of proton by AlCl4 minus from the benzene ring, and it regenerates the aromaticity of the benzene ring. Finally, it gives the product, that is the acetophenol. So this is the three steps followed by the Friedel-Crafts acylation reaction. Okay. And now we are seeing the pinacol-pinacol rearrangement. So that is what I was saying. So this is the pinacol, that is the dihydroxy compound. The hydroxy group will be present in adjacent carbons, that is the 1 and 2 adjacent carbons. Here it is present in the 2 and 3rd carbon. It should be an adjacent carbon and it should have 2 hydroxyl group. Okay. So the common name is pinacol. So when we treat this pinacol, that is the dihydroxy compound with inorganic acid. So when we treat this hydroxy compound with acid, what it produces? Respond anyone? Try to recall the last class. Students, anyone respond? At least you can see the yesterday's class note. Are you having in your hand? Are you having or not? Are you there? Yeah, correct. So when we use inorganic acids to alcohol, that acid will protonate the hydroxyl group. So it produces H2O plus. Then it removes the water, removal of water. That is correct, right? So that is what. Please have your note, yesterday's note nearby you, so that you can recall yesterday's class at least. Okay. So now that is the first step here. So when we see as a mechanism of the reaction, pinacol-pinacol rearrangement here, you see we take a pinacol as a starting material and add the acid, that is the H plus here mentioned. So when it reads, it protonates one of the hydroxyl group. Among the two, it protonates one. So after the protonation, we can see here as a oxonium ion, that is the H2O plus, name is oxonium ion. So when the H2O oxonium ion forms, it takes the bond pair of electron from this CO bond and it removes as a water. And then when this bond pair of electrons removed, you have a positive charge on the carbon, that is the carbocation, right? So this carbocation is the secondary carbocation. Secondary? Oh no, tertiary, right? So it's a tertiary carbocation, right? And this carbocation will be in order to stabilize it, it will be more. You see, even though it is a tertiary, there is a 1,2 shift here, because here we have in adjacent carbon we have an oxygen, right? So the oxygen has a lone pair here. That lone pair can give to this carbocation to stabilize even more, right? So for that, even though it is a tertiary, it the 1,2 alkyl shift happens, that is the CH3 group migrates from this carbon to the adjacent carbon and it produces the carbocation to the another carbocation. So this carbocation is again stabilized by this resonance structure. The resonance structure produces by the lone pair of electron on the oxygen. So in the next step you can see when it gives the lone pair of electron to this carbocation, it forms a double bond here, right, and it makes a plus O plus ion, oxonium ion it forms. So this is stabilized by this resonance structure. This carbocation is stabilized by this resonance structure, and to neutralize this oxonium ion, the hydrogen that will give this bond pair of electron to the oxygen, and it removes as a H plus, that is the acid, the catalyst, acid catalyst we added, right. So the catalyst H plus, the acid H plus is regenerated. That means the catalyst is regenerated here, and it gives the pinacolone, that is the ketone compound, which is the product of this pinacol-pinacolone rearrangement reaction. Okay, so we have taken starting material as dihydroxy compound, and finally it produces the ketone with change or with a rearrangement or shift of this one of the alkyl group to the adjacent carbon, right. So in this carbon we have 2 alkyl group, but in the final product we have 3 alkyl group, and the functional group is changed from alcohol to ketone, right. So this is a pinacol-pinacolone rearrangement. So please read this rearrangement very very carefully, and this is very important too. This will come for your examinations. Okay. So this involves the carbocation intermediate. So are you having any doubt? Is this clear?
Yes, sir.
Okay, fine. So the next is the Wagner-Merwin rearrangement. So all these reactions are involved with a carbocation intermediate. Okay. So you see most of things like a rearrangement. So rearrangement means there will be a shift of any alkyl group, any hydrogen atom or any of the group, it shifts from one carbon to another carbon. Okay, so that is called like a rearrangement reactions. So this Wagner-Merwin rearrangement, which occurs during the reaction involving the change in the carbon skeleton. Okay, okay, we see the starting material and we will see what is the product. So again here also the starting material will be a alcohol. Okay, so it's a simple alcohol here, which is the primary alcohol, and we use the HBr, that is the inorganic acid again here. So when we use again the inorganic acid treat with the alcohol, it produces the carbocation by elimination of the water molecule, right. So you see here the starting material is a neopentyl alcohol, that is the primary alcohol, but the product we get here 2-bromo 2-methyl butane, right. You see the bromine is, it's kind of a substitution reaction. Instead of alcohol functional group, the bromine halogen functional group is added here, but you see the shift of the alkyl group, right. The functional group which presents here in the primary carbon position, but the bromine in the product which is substituted in the tertiary carbon position, right. So that means the rearrangement is involved in this Wagner-Merwin rearrangement. So when we see the mechanism, we will understand deeply how it is the rearrangement is happen, right. The first step will be the protonation. So when we add acid on the alcohol, the protonation occurs and then it removes the water. That means a carbocation produces on this carbon. So you can see the carbocation produced here, that is the primary carbocation, right. So since the primary carbocation is not stable, so there is the possibility to form tertiary carbocation in this skeleton if this alkyl group, any one of the alkyl group shifts to the next carbon, that is the primary carbon. Okay, so here all the CH3 groups are very similar, the same CH3 groups. So among these three CH3 groups, any CH3 group can shift to the primary carbocation. So that shift we call it as a 1,2 methyl shift. Why we call it as a 1,2 shift means one group, that is which presents in the carbon number 1, it shifts to the second carbon. That means the next carbon it shifts. So that is why it is called a methyl shift. if the group is shifting, here is the methyl group, right? So that is why it is a methyl shift. If there is any other group shifts, means that is a different. For example, if there is a phenyl group here, that will be a 1,2 phenyl shift, something like that, okay, depending on the groups, okay. So here 1,2 methyl shift. So once this methyl group shifts from this carbon to this carbon, then the positive charge will produce on this carbon. So you see here, the positive charge is produced on this carbon, and this positive charge is neutralized by shifting this methyl group to this primary carbon. You see here now, when the shift happened, the generation of the primary carbocation happened on this carbon. So this is more stable when compared to the primary carbocation. So now since we added HBr, right, so the HBr will present as a H plus and then Br minus. So the H plus we used for the production of the carbocation, and remaining it will be a Br minus inside the reaction mixture. So that Br minus will attack this carbocation to make a bond between carbon and bromine. So finally you get a 2-bromo 2-methyl butane as the product. That means primary substituted tertiary substituted bromo compound as the final product. So this is called a Wagner-Merwin rearrangement. Okay, so the rearrangement happens in this step in the mechanism. Okay. So you try to the best things to remember for all this rearrangement I say you is, please remember this, you have to see what is the possibility of more stable state of carbocation in the intermediate stage. Okay, so always there will be in the first step, it will be a reaction between the starting material and the catalyst. Catalyst in the sense here we use the acid catalyst, right? So first step, acid catalyst will react with the starting material, and you have to see what is the functional group present in the starting material. So here the functional group is here alcohol. So the functional group will react with the catalyst. The possibility for this is the alcohol functional group react with the catalyst, which always produces the protonation of alcohol and removal of the water. Finally it leads to the carbocation that you can write blindly. If you see alcohol and inorganic acid both combination, blindly you can write the production of carbocation on the alcohol carbon where it presents. Okay, that is the first step. And the second step, you have to look into that whether the formed carbocation is stable itself on the carbon or not. Okay, is there any other possibility? If any rearrangement happens, is there any possibility whether this intermediate can make more stable carbocation than the recently formed carbocation? Okay, recently formed carbocation means after removal of the water the carbocation produced, right? So that carbocation will be stable or not if the rearrangement is happened. Okay, so that possibility only you have to thoroughly check. If is there a possibility, if some rearrangement happen, the carbocation will be more stable. That means the secondary carbocation which is forming after the rearrangement, that will be more stable than compared to the first formed carbocation. So here we can say as a carbocation 1, right? So if there is any possibility, then definitely you have to make a rearrangement. You have to make a shift any of the any of the groups, either hydrogen or methyl, right? So at this level, for your level, so mostly it will be a very simple group like methyl group. So you can shift the methyl groups to the primary carbocation, and then you can make a more stable carbocation. Either it may be a tertiary carbocation or it can be a carbocation which can present nearby the any atom having the lone pair. For example, alcohol here. Okay, so that carbocation is more stable. Once you drawn the more carbocation, most stable carbocation, then finally the next step will be the formation of the product, right? So you can just see the formation of the product. So once the carbocation is formed, that means that is resonance stabilized carbocation. So you just have to draw the resonance stabilized carbocation structure. That means this carbocation stabilized by the resonance and it makes a oxonium ion. And once the resonance stabilized carbocation forms, then there will be a regeneration of the catalyst. Catalyst means there is a regeneration, right? The catalyst should reproduce during the final stage of the reaction. So you initially you added a proton, and in the final step the proton should come out from the intermediate, right? So you remove a proton and finally you get the product. So this is the step. This is the step you have to carefully look into the rearrangement reactions. So can anyone tell what are the steps you have to look into carefully the rearrangement reaction? I will just tell in a very short and then followed by me. Anyone can repeat. Okay. So the first step is formation of the first step is reaction between the catalyst and then the functional group of the starting material. And the second step, after the formation of the carbocation, we have to look the possible shift, possible rearrangements where the most stable carbocation would form. Once the most stable carbocation formed means, then the next step, formation of the product by leaving the catalyst. Okay, so this is the step you have to carefully look into the rearrangement reactions. Okay, now can anyone repeat the most important steps involved in the rearrangements? Anyone, please? If people are not saying, then I will say some particular name they have to tell. Who is ready to give? Who is ready to tell? No?
Sir,
Yes. Tell Mukesh.
okay. First,
Yeah.
catalyst react with the functional group and form a carbocation, and we want to see the stability of carbocation. And second step, we want to see the lone pairs of electron and removal of catalyst and leads to formation of product.
Yeah, correct. Very good. So this is what you have to look into the mechanism and for the rearrangement process, right? So not only for this, this is the most case you have to look into in any of the reactions, most of the organic reactions. So the most stable intermediate which you can identify during the reaction mechanism, that most stable intermediate only will leads to the product. Okay, so this is what always gives the major product or minor product. When you understand the reaction mechanism very clearly, you can answer any kind of questions. For example, this is the type they will ask in the CSIR or GATE exam. When you study after your BSc, when you study the masters, then you have to appear for CSIR or GATE exam, which is very important when you go for higher studies. Okay, so there they ask all the questions related to like this only. So which product will give the major product? They will give a simple organic reaction and then they will ask what is the major product. So you have to work out the reaction mechanism. When you work out the reaction mechanism, this is the important thing you have to look into that. Okay, so what is the most stable intermediate you can identify, you can figure out in the reaction mechanism. That intermediate only will give the most stable product as a major product. So this is very basic in all the chemical reactions, particularly the organic reactions. Okay, fine. So that you strongly keep in your mind. This is the things you have to look into that in all reactions. Fine. So we have seen two rearrangement reactions. One is pinnacle-pinnacle-on rearrangement and another one is the Wagner-Merwin rearrangement. In pinnacle-pinnacle-on rearrangement, you have two hydroxy group as the starting material. In Wagner-Merwin rearrangement, you have one alcohol, that is the primary alcohol as the starting material. Catalyst is same, that is the inorganic acids. Okay, fine. So now the carbocation intermediate is completed. So in the carbocation we have seen, so what is the classification of carbocation? That is the primary carbocation, secondary carbocation and tertiary carbocation, and then generation of carbocation, right? So how we can generate the carbocation? So we have seen four type of reactions, right? After the generation of the carbocation, we can see we saw what are the reactions of carbocation, right? And then reactions involving carbocations, that is Friedel-Crafts alkylation, Friedel-Crafts acylation, pinnacle-pinnacle rearrangement, and Wagner-Merwin rearrangement. So this is the simplest thing we have seen for the intermediates carbocation. Now we will go to the next intermediate, that is the carbon ions. Okay. So carbon ion means the carbon having the negative charge. It's just opposite to the carbocation. Carbocation has the C plus positive charge on the carbon atom, which has the um, three valency, right? And now carbon ion is the just opposite. It has the three valency and it carries a negative charge on it. Okay, so as you can see here, the carbocation is having a negative charge with three valency. Okay, so here the hybridization changes. So what is the hybridization of carbocation and what is the structure of carbocation? Anyone respond?
C plus.
C plus, yeah, that is C plus carbocation. It has the positive charge. I am asking what is the hybridization and what is the structure of the carbocation?
sp2.
Trigonal,
Ah,
planar trigonal is
yes.
a structure say sp3 hybridization.
No, no. Structure is correct. Hybridization is sp2. I think Ansia, you said sp2, right?
Yes, sir.
Yeah, sp2 hybridization is correct. And the structure, Mukesh, you said right, trigonal planar.
Yes, sir.
Yeah, the structure is correct, but the hybridization is wrong. Fine. Anyway, so the hybridization is sp2 and the structure is planar trigonal. Okay. So, but here for the carbon ion, the hybridization is sp3. Why means in carbocation we have a empty p orbital, right? The empty p orbital which is located perpendicular to the, I will show the structure of carbocation. Yeah, so you see the empty p orbital will be perpendicular to the plane of the carbocation, but here in sp carbon ion, the sp3 hybridization, here you see the structure, it has a negative charge. Negative charge means it carries a lone pair of electron, right? This is unshared pair of electron on the carbon. Two electrons are there on the carbon atom. Okay, so these filled p orbitals will always locate on the top of the carbon. So because of this orbital, these three substituents, either hydrogen or any other group, alkyl group, because of this electron presence, there will be a repulsion between this filled orbital and the bond pair orbital of this three valency. Okay, three bonds. So because of that repulsion, the planarity is disturbed, and we can see here as here a kind of a pyramidal shape. Okay, so you can see it's a pyramidal shape in HL. So sp3 hybridization with pyramidal shape. So the carbon ion has sp3 hybridization and pyramidal shape. Okay, so you can see this as a structure. And then we can see the stability. Next we will move to the stability of carbon ion. So what kind of group can stabilize the carbocation we have seen? Electron withdrawing group can stabilize, or electron donating group can stabilize the carbocation. Which group can stabilize the carbocation? Anyone tell?
Electron withdrawing, sir.
No, wrong. donating group can stabilize the carbocation? Carbocation only I asked, right? Or carbanion?
Sorry, sir, I said for carbanion.
Okay, carbanion. Carbanion means whatever you said, that is correct. Okay, so it's just opposite to the carbocation. Carbocation will be stabilized by electron donating group, and similarly, just right opposite, carbanion will be stabilized by electron withdrawing groups. Why? The same reason. So you have a electron rich center, the C minus, which has a 2 electron, which is kind of electron rich center. So when there is a electron withdrawing group presents near to the carbanion, what it will happen? The groups which presents near to the electron rich center, that try to pull the electron density of the carbanion, right? So if one group presents, that can pull relatively, and two group presents means that can again pull relatively more, and 3 electron withdrawing group presents means that can most probably pull by all the 3 groups, electron withdrawing groups, so that the carbon rich center may relax, or it can the minus charge will be distributed among 3 electron withdrawing groups, so that it feels relatively more stable. That is what the example yesterday I have given, right? For example, if you are carrying a 40 kg of weight, if one people helps, you will be relaxed a little bit. If 2 people are giving you a hand, then you will be relaxed a little more, and if 3 people are giving a hand, then you will be relaxed more, right? So like that, you can directly relate this electron density, you can compare with the 40 kg, like kilogram, right? So when there are more people to give you a hand, then you are more stable, right? Similarly, there are more number of electron withdrawing group to share the electron density of the carbanion, means the carbanion will be more stable, right? So that is what the concept here, how the carbanion stabilized by the electron withdrawing group. Electron withdrawing group means here we can say minus I inductive effect. Okay, so examples of electron withdrawing groups, what we can say, nitro group or cyano group, C triple bond and cyano group, right? So those kind of group we can say as a example. Okay, and here are the pKa values. pKa values in the sense, we can directly relate the carbanion stability. Each and every carbanion has different kind of value. For example, the acid strength, right? Each and every acid has a different strength. Like that, the carbanion has its own strength. The base strength, we can say. Carbanion means C minus. When there is a negative charge, we can say that as a base. Okay, so each and every carbanion has different kind of pKa values. Okay, I think this we no need to go into very deep, that we can skip now. And now we can come for the stability of carbocations, which depends on the following features. So what are the factors which affects the stability of the carbanion, right? So in carbocation we have seen the 4 factors. Similarly, in carbanion also we will see the 4 factors. One is electron withdrawing inductive effect, and conjugation of lone pair of the carbanion with multiple bonds, and third one is the aromatization, and fourth one is the increase in the S character in the carbanion. Okay, so here we are going to see a new one, that is increase in the S character. In carbocation we have not seen that, but here in carbanion we are going to see this new one, right? So all the 3 above the 3 we have seen for the carbocation. So the electron withdrawing inductive effect, so that is what I was explaining now. So if we have a minus I inductive effect group, that is the electron withdrawing group, for example nitro compound CN or carbonyl compound CO, right? So this kind of electron withdrawing group presents nearby the carbanion, that stabilizes the carbanion, right? But if we have electron donating group or plus I effect group, for example alkyl group or methoxy group, Any electron donating group means that destabilizes the carbanion. Okay, that is the very less stable carbocation, as you can see here, right? Okay, so you can see the carbanion stability here. The primary carbanion will be more stable. So here minus charge will come. Sorry, I didn't put here minus charge. C3 CH3 minus here. The simple methyl carbanion is the most stable when compared to the primary carbanion and secondary carbanion and tertiary carbanion. So sorry, there is a minus charge in all the things. I didn't put, so when I share I will edit this and I will put the minus charge here. Okay, so here the tertiary carbanion is the most least stable carbanion. Okay, which is directly reverse opposite trend of the carbocation. In carbocation, tertiary carbocation is the most stable, but in carbanion, the tertiary carbanion is the least stable. Okay, so the most stable is the methyl carbocation without any functional group, without any alkyl group. Okay, so it's based on the inductive effect. And next is the conjugation of lone pair on the carbanion with multiple bonds. So this conjugation effect plays very important role. Okay, as you can see here, when the base attracts the proton, it generates the carbanion. So here you have a group. For the conjugation you need, yesterday I said we need any pi electrons or lone pair of electrons. Without these two the conjugation will not happen. So here we have C triple bond C as the pi electrons. So using this pi electron we can have a conjugation here. So once the carbanion is formed, this is most electron rich in center, so this will try to give electrons to the adjacent group. So particularly if we have the electron withdrawing group, definitely it will give to the near the electron withdrawing group. So this minus charge will be transferred to this nearby this C triple bond end group. So when this group shift to here, then you will have a double bond here, and among this triple bond, one bond will go to one bond will shift, the lone bond pair of electron will shift to the on the nitrogen atom. Okay, so that you will have a minus charge on the nitrogen atom. So you will have a kind of resonance structure. I will just share the whiteboard and then I will just draw the mechanism how it can be. So now you can see the whiteboard, right? Can you see the whiteboard now? Okay, fine. So I just draw here. So carbon, no, it's not. Sorry, since I am using a mouse, so it will be a little. Okay, so carbon minus here, and C triple bond N. Oh, I am using a mouse, it is not coming good, so please adjust. Okay, so now, so this will shift here and this electron will shift here, so that you will have a C double bond C, and this triple bond lone pair of electron will be transferred to on the nitrogen atom. So you will have a double bond nitrogen and minus charge here. So this will be kind of a resonance structure, right? So you will have a resonance structure. So this will be this carbon ion will be stabilized by this resonance structure with any kind of with any kind of any pi bond or any kind of lone pair electron groups. Okay, so here you can see this will be stabilized like this, and similarly instead of C triple bond C, here we can having carbonyl group, right? Similarly the carbonyl group will go for the resonance structure, as you can see here. So this um, uh, minus charge will shift here, and among these two CO bond, one bond pair of electron will go on the oxygen and it produces the minus. Okay, so right like this, and similarly for the nitro groups, so it produces the minus charge and it comes here, and one of the bond goes here on the minus charge. So this conjugation or lone pair of electron will increase the stability of the carbon ion. So there are common things. This is the very common thing. Either it can be a carbocation or it can be a carbon ion. So now can you see whiteboard, or you can see only or you can see my PDF? Which one you are able to see now?
We can see both, sir.
PDF, right?
Right, right.
Sorry, I couldn't hear you clearly. Now you are seeing a PDF or whiteboard?
Whiteboard.
Whiteboard, sir.
Whiteboard only. Okay, then I have to stop sharing, I think, whiteboard. Okay, I am just stop sharing the whiteboard, and now I am showing. Now you can see the PDF, I think, right?
No, sir.
No? Which one are you seeing now?
Your video.
Oh, stop sharing means it's completely gone now. Okay. It's very difficult. Okay. Now we can see the PDF, right?
Yes, sir.
Okay.
Yes.
Okay. So now, as I said, the C triple bond C, that is the CN group, right? So that will stabilize through this. Similarly, the CO group will stabilize like this, and nitro group will stabilize like this conjugation. So the conjugation or lone pair which presents near to either carbocation or carbon ion, whatever it may be, the conjugation will stabilize both the carbocation and carbon ion, right? So this is common, but inductive effect it is a very different, and then the stability is different, that is the opposite trend, right? But the common thing is the conjugation and the lone pair electrons, right? This both thing will stabilize both the carbocation as well as carbon ion. And then this also a common aromatization. There also we have seen the carbocation stability by aromatization, and in carbon ion also the aromatization will make the carbon ion as a stable, right? So here in the last example yesterday we have seen there is a tropylium ion which has 7-membered ring and which has one carbocation in that, right? So that is having total of 6 pi electrons with one ring, right? That is aromatic compound. And similarly here we have a cyclopentadiene, that is the 5-membered ring which has 2 pi bond. That means total of 4 pi electrons are there. So if you remove one of the proton, and this CH2 is not in a conjugation, so if you remove one of the proton and it produces the carbon ion on this carbon, okay? So now this carbon ion means it has a 2 unpaired electrons, right? So that means it may come in the category of pi bond, right? 2 pi bonds are there without any pairing. So now total number of pi electrons are 6 for this ring, right? So 4 pi electrons which all are bonded and 2 pi electrons which are non-bonded. So total 6 electrons. Again this is a planar compound, so this will go and this will undergo Huckel's rule, 4n plus 2 pi electrons rule. So this will act as a aromatic compound, whereas this simple 5-membered ring, that is the cyclopentadiene which has the 2 CH2, this is not in a conjugation. This is not a aromatic compound. This is anti-aromatic compound. And after removal of one proton, and this act as a aromatic compound. So when there is a formation of aromaticity by removing one proton or any other group, that compound will be more stable. So this where the formation of carbanion which makes the compound as aromatic compound, that compound is more stable, and this carbanion will be most stabilized. Okay, so this is the stabilization by aromatization. Okay, and similarly the benzyl carbanion. Yesterday we have seen benzyl carbocation, and here benzyl carbanion, right? CH2 minus here we are going to see. So this also will be stabilized by the aromatization and resonance structure, right? So this will be stabilized. So here you can see the groups. What are the groups can stabilize the most stable the carbanion? For example, you are having a different kind of functional group. If the nitro group presents, that stabilize the that makes a most stable carbanion. And if we have a keto group, or if you have a keto group, that stabilizes the next, and then ester group, SO2, sulfur dioxide, and then CN, then amide, halogen, hydrogen, and then finally R. Okay, so when you have a alkyl group, that is the R group, that is the least stable, and when you have a very very strong electron withdrawing group, that is the NO2, that is the most stable carbanion. So it is a just order of functional group which stabilizes the carbanion. And the fourth one is the increase in the S character in the carbanion. So S character means we talk about by the hybridization. Okay, so there are three types of hybridization, right? sp3, sp2, and sp hybridization. So here I written sp1, that is not sp1, that is a sp hybridization. So you can consider as a ratio, sp3 means there is a 4 orbitals, 1 s orbital and 3 p orbitals involved, right? So if you take the ratio, 25% of the s orbital and 75% of the p orbitals, right, involved in the sp3 hybridization. But when you come for the sp2 hybridization, so 1 s orbital and 2 p orbitals involved, right? So that means totally 3 orbitals involved for the sp2 hybridization, right? So that means if you take the ratio, S will be having 33 and P will be having 33%, that means each p orbital will be having 33%. So total 66% of p orbitals and 33% of s orbitals, so which means 99%, and the 1% again will be divided. So that means we can say 33.33%, right? So when you come from sp3 to sp3 to sp2, the s character increased, right? As you can see the ratio, in sp3 you have 25% of s orbital, and in sp2 you have a 33.33% of s orbital, and when it comes to sp orbital, you have a 1 s orbital and 1 p orbital. That means the ratio is 50-50 ratio, 50% s orbital involved and 50% p orbital involved. So the s character increases when you go from sp3 to sp hybridizations, right? So when this s character increase, that will stabilize the carbanion. For example, you have a alkane. Alkane has cs3, right? Methyl ethyl. The simple alkane has sp3 hybridization. Here the s character is only 25%. But when you go for alkene, that is CH2 double bond CH2 unsaturated compound, where it has the sp2 hybridization, where the s character is 33%. So compared to alkane, alkene will stabilize the carbanion relatively more. Okay, but when you come to alkyne, that is the CH triple bond CH, where the carbon has s character of 50%. So this alkyne can stabilize the carbanion the most. Okay, So compared to alkene we stabilize more, and compared to alkyne will stabilize more the carbanion. So this is the example and the trend of the carbanions, right? So the alkyne stabilizes the more the carbanion, and then next the least stable is the alkene, and then next the least stable is the alkene. Okay, so this is the order. So these are the total 4 factors which stabilize the carbocation. So the first one will be the inductive effect, right? So that is the electron withdrawing or electron donating. So the electron withdrawing groups will stabilize the carbocation, and second one is the conjugation or resonance structure, right? So the resonance structure or conjugation stabilizes the carbanion, and third one is the aromatization. So by making a carbanion, if it produces a aromatic character, that will be stabilized. And the fourth one is the increase in the S character. If the S character increases in the carbon, that carbon stabilizes the carbanion, C minus. Okay. And then next we see generation of carbanions, how we can generate the carbanions. So the following methods are used for generation of carbanions. So first thing is from alkyl halides. So in carbocation also we have seen the first example from alkyl halide. There we used alkyl halide, but in the presence of silver salt A plus. But here we use some metals. Okay, means here also we use a metal like Mg, but this is an electro, what it say, okay, it's kind of a different. Okay, so how it different, I will say. So magnesium we use here as magnesium. So we use here as a magnesium. So when this magnesium reacted with alkyl halide, it makes a Grignard reagent. That is the very famous reagent you might have studied in +1 and +2, right? So this magnesium immediately reacts with the alkyl halide, and it makes the alkyl group more electronegative. Okay, so where it can produces the carbon ion, okay, as a R minus. So this is one of the method by Grignard reagent method. So we can produce the carbon ion of alkyl halides. And the second method is the abstraction of proton by a base. So when you add a base to a particular substance or in an aromatic compound where there is a possibility to produce the carbon ion. Not all the alkyl compounds will produce the carbon ion, where it can have a little acidic character, or it should have a halogen atom nearby that. So in that sense, in that carbon atom only the base will work and it will remove the protons. So in this case we are having example para-nitrotoluene. So para-nitrotoluene means the nitro compound acts as a highest electron withdrawing group, as I say. So because of the electron withdrawing nature, the whole benzene ring will act as a electron withdrawing compound. So when you add a base, so this CH3 group will easily give one proton to base, and then it produces the carbon ion, as you can see here. So if you take a simple toluene and add base, it won't go that much easily. But if you have a nitro compound on the phenyl ring, particularly at the para position, it will act as a base, and it can easily donate proton to the base. Okay, so it produces the carbon ion. So this is one of the method by adding base. The commonly used bases are sodium hydride or ether conditions, or sodium aqueous sodium hydroxide, or sodium tertiary butoxide in tertiary butanol, or N-methyl pyrrolidine in ether. So you can just remember the bases, that is sodium hydride, aqueous NaOH, and sodium tertiary butoxide, potassium tertiary butoxide, or sodium tertiary butoxide also you can use, sodium or potassium salt of the tertiary butoxide. Okay, and then N-methyl pyrrolidine. So these are the common bases we use for the production of the carbon ion. And then from unsaturated compounds, for example, you take any unsaturated compound, alkene or alkyne. Particularly the alkyne will generate the carbon ion very rapidly because of the S character which we have seen just before, right? So addition of a nucleophile to an unsaturated compound generates the carbanion. So if you take some nucleophile means it wants a nuclear site, that means it wants a plus, where the plus charge is there, that will go and it will attack. So usually the nucleophile carries a negative charge, okay. So that nucleophile will attack the double bond or triple bond, and it produces the carbanion by I will just, okay, if I share the whiteboard again it will go, okay. So just this minus charge will attack here, and the double bond of this lone pair electron will go on this carbon, so it will produce the carbanion. Fine. So these are the simple three methods we produce the carbanion. One is from alkyl halide, and another one is from any compound which treat with the base, we produce the carbanion, and another one is the treatment of nucleophile with the unsaturated compounds. And reactions of carbanions. So what are the reactions the carbanions can go? So first and famous reaction is the elimination reaction, okay. So as I said before, when you add a base to an organic compound, either there should be any electron withdrawing group nearby that, or there should be any halogen compound nearby the carbon, right? So here we have a halogen, and near to that, that is the alpha carbon, we would say. The functional group is bromo here, so the functional group carrying a carbon, alpha to that, the base will remove the proton. So once the base is removed the proton from the alpha carbon, it produces the carbanion. So that carbanion, the lone pair of electron will be given to the next carbon. So since here the halogen will act as a leaving group, so immediately this Br minus will remove, the bromine will remove as a Br minus by taking the bond pair of electron of this Cbr bond. So it will remove as a Br minus. So you can see here as a double bond. So it's an elimination reaction. Why it is called elimination means you are eliminating one hydrogen and one bromine by adding a base, right? So you are removing one hydrogen from one carbon and one bromine from another carbon. So when you remove one group from each carbon, there will be a double bond presence with the both the carbon from where the hydrogen and the functional group is removed, right? So that is why it is called an elimination reaction. By removing the two groups or two atoms, you are making a product. That is called an elimination reaction, okay. So mostly the elimination reaction gives the unsaturated compounds, that is the double bond or triple bonds, okay. So this is one reaction, and then reactions involving carbanions. So this is the major reaction. Then finally we will go again the reactions involving carbanions. The first is the aldol condensation, okay. There are so many number of reactions. Here we are going to see aldol condensation and Erskine reaction. Two reactions we are going to see here, okay. The first is the aldol condensation. So here we say condensation. Condensation means the two groups become added and then generates a one group by removal of a simple molecules. For example, removal of water, or removal of carbon dioxide, or removal of carbon monoxide, something like that. A simple removal of group which unites two groups. For example, here we take two aldehyde groups, and by removing the water we will have a compound like the aldol, that is called beta hydroxy butyraldehyde. So that is the aldehyde with alcohol group. So in the starting material you have two aldehyde group, and in the final compound you have a aldehyde and a new functional group of the alcohol, right? So by removal of the water, the functional group is changed for one of the aldehyde, from aldehyde to alcohol, right? So this is kind of an aldol. This is a condensation reaction. The name is aldol reaction. There are so many condensation reactions, and among them aldol condensation is very important and very easy to. Okay, I think we will do it in our practical also. So I study this reaction. Two molecules of aldehydes react in presence of a base to give a product called aldol. So for this reaction we need a base. Okay, so the base will be either aqueous sodium hydroxide or some other bases like sodium tertiary butoxide or potassium tertiary butoxide. So when we look at the mechanism, so first as I said, whenever you are having a catalyst or catalyst, the catalyst will react with the starting material, right? So here the catalyst is the base. Base is means hydroxy, right? Sodium hydroxide means OH minus, that is the base. So the OH minus abstract a proton from alpha carbon to the functional group, right? The functional group here is the aldehyde. So the alpha carbon is the CH3, right? From the alpha carbon the base removes one proton and it produces the carbon ion here, right? So here you can see the carbon ion is produced minus. So once the carbon ion produced, if you are having adjacent any resonance structure, kind of double bond character or lone pair structure, that will be stabilized by the resonance, right? So here in adjacent you have a C double bond O, so that will be a key resonance structure. So this minus charge will go to in between the C and C single bond, and when it goes here, the double bond between C and O, bond pair of electron will go on the oxygen. So oxygen will get a minus charge. So you can see in the next step, the double bond comes here. So there is a double bond formation between carbon and carbon, and when this lone pair of electron from C double bond O, it moves to on oxygen, you get a single bond here, and oxygen carries a minus charge, right? So this is a resonance structure. So once this kind of resonance structure happens, this will be stabilized. This carbon ion is stabilized by the resonance structure. Okay, so apart from that, there is no any other possibility of carbon ion which can be stabilized more. Okay, so as I said in the last Wagner-Merwin rearrangement, for the carbocation we have to look the most stable state where the possibility of the carbon ion or any intermediate it form where it will be most stable, right? So here you have only one possibility, the carbon ion formation on this CH2 carbon, that will be stabilized by this resonance structure, right? You have only one carbon which will be stabilized by the resonance structure, right? So that is resonance stabilized. So now this resonance stabilized carbon ion will attack the second molecule of the aldehyde. Okay, so now this carbon ion acts as a nucleophile. Nucleophile means it needs a electron deficient center. That means it needs a positive charge. Where there is a positive charge or electron deficient center, okay, that place this C carbon ion will go and attack, right? So because this C minus means it's an electron rich center, now it needs an electron deficient center. So now in the second molecule of aldehyde, the electron deficient center is this carbonyl carbon. As in the C double bond O bonds, the oxygen is more electron group, you know, right? So because of the oxygen withdrawing nature or electron deficient in nature, this oxygen will pull some of the bond pair of electrons towards the oxygen. So there will be always a partial positive charge on this oxygen and partial negative charge on the partial negative charge on the oxygen and partial positive charge on the carbon, right? So there will be a small positive charge on the carbon. So that means this C minus, that is the carbon ion generator, will go and attack this carbon of carbonyl compound where there is a partial positive charge is there, right? So when it attacks, then this double bond, the double bond of the lone pair of electron will go on this oxygen. So in the next step you can see here, see this CH2 minus attacked here, so that the bond formation between this carbon and this carbon is formed, right? So CH2 and then CH. So once this bond pair of electron moved on this oxygen, you have a minus charge here. So CH3 C, CO minus, and then CH2, CH3 CH, CO minus, CH2 CO, this COH, right? So you will have one, the two molecules become one molecules now. So in this process what happened, that we will see the next. Okay, so now once this minus charge is on the oxygen, now what will happen is, so when there is an attack from this, the first step, the OH minus attack this proton, right? So there is a formation of water, because the H plus proton means H plus, it attacks and then it takes the proton, so that means H2O, the water formation is there, right? So it removes as a water, H2O. Now again it's a base catalyzed reaction, the base has to regenerate, right? So that means OH has to regenerate. So now the formed anion, that is the alkoxide anion O minus, which will abstract a proton from the water which is removed, right, from the starting of the reaction. From there, from the water it will abstract one proton, and then the OH minus is regenerated, that is the alkoxide ion is regenerated, hydroxide ion is regenerated, not alkoxide, hydroxide ion is regenerated. So now it has a alcohol, that is the aldol, beta hydroxy ketone or aldehyde, beta hydroxy carbonyl compound. See, beta means with respect to the functional group, that is the beta carbon. So the functional group here is the aldehyde, that is the major functional group, and the alpha carbon is CH2 and the beta carbon is CH, right? So the beta carbon is having a OH group, that is the alcohol group. So that is the beta hydroxy aldehyde. So that is called the aldol. Okay, the general name of this is called aldol. Okay, so this is a condensation reaction. So the condensation reaction happens by base catalyzed reaction. So when you add base to the one molecule of aldehyde, it abstracts a proton from alpha carbon and it generates the carbon ion. The generated carbon ion is resonance stabilized. So this carbon ion is stable. The stable carbon ion attacks the another molecule of the aldehyde with the position of the carbonyl carbon, and then when attacking there will be a union of this. That means two molecules are attached together by bearing a negative charge on the oxygen. This negative charge of the oxygen takes one proton from the water and it generates the hydroxide ion, or it generates the catalyst. Okay, and finally it gives the product, that is the aldol. So this is the mechanism of aldol condensation reaction, where the carbon ion is involved. Any doubt? Okay, if there is nothing, then we go to the another reaction, that is called a Perkin reaction. Okay, so in Perkin reaction it involves the reaction of an aldehyde, say benzaldehyde, okay, with acetic anhydride in the presence of sodium acetate. Okay, so acetic anhydride first reacts with sodium acetate. Okay, so we will just see the two starting materials and the base. Okay, so here the starting materials are, one is benzaldehyde, right? So in the last example we have seen the acetaldehyde CH3, that is the aliphatic aldehyde, and here we are going to see as a aromatic aldehyde, that is the benzaldehyde. And the another starting material is the acetic anhydride. So acetic anhydride means it's a derivatives of acetic acid. When there is a two acetic acid molecules combined together and removes water, it produces the acetic anhydride. Functional group of the anhydride is COOCO. Okay, so this is the functional group of the acetic anhydride. So when we add base, The base is here sodium acetate CH3COO minus Na plus. Na plus means that is the sodium salt of acetic acid. So in the sodium acetate salt, the acetate anion is the acting as a base. So this acetate anion abstracts one proton from this acetic anhydride. So when we add this, first thing, because there is no alpha proton in the aldehyde to abstract a proton, right? In the last case we have CH3CO, right? The CH3 has a one proton which can easily abstract by the base, but here we have a phenyl group here C6H5 as a phenyl group. From phenyl group we cannot remove a proton as easily like CH3. So there is no possibility to remove proton from this benzaldehyde. So this base will remove a proton from this acetic anhydride, since we have CH3 group here near to the carbonyl carbon. So this will equally remove. So this CH3 group or CH3 group which is placed near to the carbonyl carbon or electron withdrawing group, that is called active methylene carbon. Okay. So why it is active methylene means since there is electron withdrawing group near to that, so it is more active. Active in the sense it is ready to give proton. When you add a base, it is ready to give a proton because of the presence of the electron withdrawing group adjacent to that. Okay, so that is why it is called active, because it is very active to give proton when you add some base. That is why it is called active methylene group. Okay, so when you add proton, immediately this active methylene compound, that CH3 adjacent to the carbonyl compound, which gives one proton, and it forms immediately the carbanion. So once again this carbanion formed means it will ready. We have to look the stability, how it will be stabilized, right? So since it has adjacent CO carbon, and this will go to the resonance structure as we have seen in the last case. So like that it will go for the resonance structure, and this will be stabilized by the resonance. So this formed carbanion is stable, and there is no any other possibility of the more stable carbanion. So that is the only possible stable carbanion formation, and this stable carbanion will react with the aldehyde carbon, as the aldehyde carbon which always carries a partial positive charge. This carbanion attacks the carbonyl carbon, right? And then when it attacks, definitely the double bond from the CO double bond, one bond pair of electron will go or move to the oxygen atom. So that means oxygen will carry one negative charge, right? So this negative charge will be again attacks the protons where we removed water or acetic acid. So in this case the acetic acid will form when the proton is obstructed by this acetate anion. It forms a acetic acid. So this alkoxide anion will take one proton from the acetic acid. What happened? It forms the acetic acid, and this alkoxide ion abstracts proton from the acetic acid, and it regenerates the acetate anion, right? And then finally we will have the product as a hydroxy compound with anhydride, acid anhydride functional group. So again from that again this will not be ideal, this will not be a stable product, because since the acid anhydride is there, it is not very stable. So the detailed mechanism I will show in the next class when I talk in the board. Okay, I will show the detailed mechanism. So again the base will attract proton from this, since it has more CH2 groups. There are again active methylene hydrogens are there, which can be easily abstracted by the which can be easily abstracted by the base. So it can produce carbanion here more again. Okay, so that again the reaction will happen, kind of again circle will happen here, and then there is a removal of water from OH here and one hydrogen from here. So when you remove water from this two, you will have a double bond here. So once the double bond is formed, then with the water this anhydride group will be hydrolyzed and you will get a acid group here, carboxylic acid group here. So finally you will get a cinnamic acid as a final compound. So I will write a detailed mechanism uh, in the classroom, in the board, so that you will understand. But in the exam, I will write for your understanding, but in the exam it's not necessary to write for you the mechanism. You can just write this mechanism for the mechanism for but you no need to write very detailed in the exam. Okay, that is fine. So the final product will be cinnamic acid. So you take a starting material, benzaldehyde and the acetic anhydride in the presence of sodium or potassium acetate, and final product you will get as a cinnamic acid. So this is called a Perkin reaction. Okay, so with this the carbon ion intermediate is finished, and then we will see next the free radicals. Okay, that we will see tomorrow or the Monday we will see in the class. Okay. So up to now, if you have any doubt, so you can just ask or we can share. Any doubt?
No, sir.
Okay.
Sir,
Yeah.
what is the use of this cinnamic acid?
Cinnamic acid. There is no particular application or there is no particular use, but it's an unsaturated carboxylic acid of aromatic unsaturated carboxylic acid, we would say. So there is no particular use of cinnamic acid as far as I know. It's a
Okay,
reaction,
sir.
just a reaction where we need it can be used for some of the starting material for some other purposes, or it can be a method of preparation of cinnamic acid using Perkin reaction.
Okay, sir.
Okay. Okay. So if there is no any doubt, then we will stop it here, and we will continue our class on Monday. Okay. So see you in the next class. Bye bye, students.